three elements in this model. Try to make an abstraction. So we have a finite length fracture in the rock, and this fluid is filled in the fracture. And now you have a source, which is like a perturbation of the teleseismic wave. So then this is the model. Then we ask one question. The question is, if there is a perturbation here in the fluid, or maybe in the solid as well. So for now let's consider there's a pressure disturbance in the fluid, and what is the fluid pressure at the fracture tip? Okay, so if it's zero frequency, if you have 1 Pascal fluid pressure change at the tip, it should be 1 Pascal. So they have to be equal. But when you have a dynamic wave, this may be different. Okay, actually it turns out this is a very, very challenging question to answer. It depends on a lot of things, including the geometry of the fracture itself. So what I can tell you is what I found in numerical modeling is the pressure at the fracture tip can be magnified by 2 orders of magnitude. So which means if you have an incident wave which is 1000 Pascal, 2 orders of magnitude, you can get to 10 to the 5th. So if it's 10,000 Pascal instance pressure, and then here you can get a 1 megapascal range. So we call this pressure surge phenomenon, or PSP. So to solve this problem, we have to do really modeling. Okay, this is applying Hooke's law and Newton's law at the microscopic level. So the fracture thickness is usually very small. It's only on the order of millimeter. So, but the fracture itself is long, so 20, 30 meters. So therefore, when you do the modeling, it's very challenging to consider different orders of length scales. So if you do finite difference, you have to discretize your model at sub-millimeter grids. But then the length is very long, so you have too many grids to solve in a finite difference solver. So in order to understand this problem or solve the pressure propagation from this fluid reservoir to the tip of the fracture, I used a hypersingular boundary element method I developed while I was at MIT. We published a paper with Mike at Geophysics. So that is a method we can solve wave propagation or wave interaction with a long, skinny fracture fluid field. So first I did some benchmark comparison of waveforms with spectral element code. But in that case, I use a very thick fracture wave. So here's 100 meters long, I think it's 10 meters thick, but this is only for benchmark purpose. We have a source in here, and we put the receivers in the fracture to record waveforms. So basically in the fluid region, this is a frequency domain method. We solve the Helmholtz equation. And in the solid region, we solve the Navier-Stokes, the solid equation. And along the fluid-solid boundary, we apply the boundary condition, continuity of normal traction, and normal particle velocity. So just to ensure the boundary is continuous. There's no separation of the interface or no crease over each other. So here's the comparison of the two waveforms computed by the boundary element and the spectral element. So this is the receiver position. Here is 0. Here's the 100 meters. So we put the receivers in the fracture, and we calculate the boundary element waveforms and the spectral element waveforms, and they are identical. So therefore, this boundary element code is valid to investigate this problem. Unfortunately, if you make the fracture very thin, the spectral element has difficulty to compute, because you have to decrease the grid to sub-millimeter, and therefore it's a domain method. Even 2D, it takes a very long time to compute. But on the other hand, the boundary element is following the geometry of the boundary. And instead of solving a 2D domain problem, it solves a 1D matrix problem. So that's why it's faster. So here are some results. Okay, so I considered a fracture with 2 millimeter aperture, 8 meters long. Okay, still the same geometry, but decreased the aperture to 2 millimeter. And here 0 is the fracture, the beginning of the fracture. 8 is the tip of the fracture. So same set of waveforms, just filter them into different frequency band. So I put this T shape just to show you the fracture geometry. This side is the reservoir, and this long, skinny is the fracture. So what you see is, if I filter the frequency into 0.3 to 0.6 frequency band, and these are vertical is the waveform, horizontal is the position of the receiver. So in the beginning, the amplitude wave is 100 times compared to the instant wave pressure. And 1.2 to 3 hertz, so the amplification factor is 40 times. And here is around 10 times for 3 to 5 hertz. 8 to 12 hertz, we got a 20, but here you can see there is a mode that's a higher harmonic developed for the waves along the fracture. And here is 12 hertz to 16 hertz. Again, this is a note. It's like wave propagating along a fixed guitar string. So you got this overtone. And here 15 to 20 hertz. So the idea is, at low frequencies, the pressure in the fracture, the fluid pressure in the fracture versus incident wave pressure can be 100 times, more than 100 times. So this is a fracture, the pressure magnification effect we talk about, and they are frequency dependent. So,
is it clear what sets the frequency at which it turns around? The amplitudes sort of decrease and then start increasing again.
Right.
Is it clear what sets that frequency?
It's the resonance. So basically in nature, we observe this low frequency amplification more than the high frequency. But in the model, we also predict there is a high frequency magnification. So therefore, we can do experiment in the laboratory to verify this frequency range, which is not observed in nature. So same theory, but the theory covers both low frequency and high frequency, and you have laboratory to verify the high frequency end. So to either validate or refute the theory.
Do you think fracture roughness would have any impact?
Fracture
roughness?
I don't know. I think they should have some effect.
I kind of wonder if that would kill your high frequencies preferentially.
Right. But I can do a modeling. It's just to design a model and run the code.
Because there would be a lot of dissipation on the fractures.
Yeah. So I have to see, in the fluid I didn't put any viscosity in it. So no viscosity, just the water. So the other one is so I'm going to show you a movie. Those are just the static waveforms. So again, this side, this box is the reservoir, and here is the fracture, here is the tip. So this line shows the pressure variation in the fracture as a function of time. So that's a movie. So, and these are the waveforms filtered at that frequency band. So at 0.3 to 0.6. So as time goes by, and what you can see is the pressure in the fracture, the increase and then the decrease, increase, decrease. So simultaneously, okay? So the sense of motion is equal for all the points within the fracture. And what this means is the pressure in the fracture either elevated or decreased. I'll show you again. So again, you can see it's like a syringe. You just squish the fluid in and out, in and out. So that's why the low frequency probably can enhance the permeability, because there's the net pressure gradient within the fracture and outside. Okay, when you have a net pressure gradient by Darcy's law, that will induce a flow between the fracture and the outside. So once you induce the flow will flush out the particles stuck in the fracture and to clear the pathways for fluid flow, and that will increase permeability. Okay, that's the theory here, is when we have low frequency instance at the right frequency, the entire fracture pressure got increased or decreased simultaneously. Of course, this end is going to be more, so that's why you have the gradient of the pressure. And people actually have done a fractured sandstone experiment in laboratory, and they do observe increase of permeability when you oscillate the sample while you flow the fluid through the fracture. So how about high frequency? So now, right now this is at 12 to 16 hertz. And in this case, because this node, we got a alternating high-low pressure in the fracture. So when you average the pressure within the fracture, you pretty much get zero because it's high-low alternating. So if you consider in and out of the fracture, you don't have the gradient. And here is even higher frequency, 20 to 30 hertz. And what you see is this, there are several nodes, so they just go wild, up and down, up and down. So eventually, you don't have a net pressure gradient drive the fluids flow in and out of the fracture. So high frequency, according to this, are not going to promote permeability. You have to have the low frequency. Of course, for this specific geometry of the fracture, 2 millimeter and 8 meter long.
So what kind of sources did you input? What kind of
It's a delta function. It's a band limited delta function. So
in the space, is it still 1 point?
Point source.
So like if we think about the dynamic triggering, then entire area must
Possible,
be
yeah.
same phase for the low frequencies and high frequencies.
Oh, it's a point source, but it's very far from the fracture. So I put the source far.
So
Yeah.
not inside this area.
No, the source is outside the fracture, not inside. It's outside the fracture. Because the reason I didn't put a plane wave, usually we should put a plane wave, is the boundary effect. So therefore, I just put the point source far away from the fracture. So those are some time domain waveforms, and we do see pressure magnification. We see the distribution of pressure inside the fracture, and at the low frequencies, you can have net pressure gradient in and out of the fracture. So this figures, what I show is just transform each seismogram into a frequency domain. So it's like a mono frequency, single frequency. So your source is instead of a delta function, but it's a sinusoid, just shaking at one frequency. And so for this one, the fracture aperture is still 2 millimeter, but I changed the length of the fracture. So this plot A is 1 meter long, 4 meter long, 6 meter long, 8 meter, 10 meter, 12 meter, 14, 16, 20 meters. So same aperture, but change the length of the fracture. And you recorded the waveforms, and for each waveform you do the Fourier transform. So vertical axis now is the frequency in hertz. Horizontal axis is the position of the receiver. So again, we define the magnification factor, pressure surge factor, as the fluid pressure in the fracture over the instant wave pressure. So that gives you a ratio. This again shows the relative geometry between the reservoir and the fracture. So this is a very short fracture, longer, and this is 20 meters. So what you see is you change the geometry of the fracture, and the response is different. They're frequency dependent. So if you have very short fracture, the fluid pressure inside the fracture is only magnified by 8 times. So that means if you instant pressure is 1,000, now you have 8,000. So not much, still very small. And if you have 4 meters long fracture, your magnification can be more than 600 times. So again, that can give us the right magnitude comparing the incident pressure and the pressure needed to trigger earthquakes, or the earthquake stress drop. So again, this one, 6 meters. And around here, so 8 meters, so the low frequency can magnify 500 times. So when you go to a longer fracture, the waves just slosh back and forth, so you develop a node around 5 meters. So this is the first overtone. And clearly you have more overtones when you get a very long fracture.
It's like a building rotated by 90 degrees.
Yes.
Like Tom and me.
Yes.
And we are just like our quick building projects.
Yes. So what do you see? The frequency, for example, this one is less than 1 hertz. So you should get 500 times magnification. In this case, so for example, the 4 meter case is around 8 hertz. You got a very large magnification. And it's very sensitive. Okay, if you go to 7 hertz, 0. There's no magnification. Very small magnification. So the magnification factor depends on the geometry. Clearly, it depends on geometry and depends on frequency very sensitively. So if you turn the problem around, so if I get a frequency response of the fracture, I can tell you the fracture size and the geometry.
Sorry, you may have to mention this, but what is the order of magnitude of the fluid pressure?
Oh, these are ratio.
That is-
This is a ratio because we are solving a linear elastic problem. It doesn't matter what is the incident. So you let's assume the incident is 1, and now you have recorded the pressure in the fracture, and you do a ratio, and that's like 300 times magnification.
But like in a typical field scale hydraulic fracture, what is the order of magnitude of pressures of the fluids that are interviewed?
So this is not this is the perturbation of the pressure due to seismic waves. So without seismic waves, you have a hydrostatic fluid pressure in the fracture, and that depends on the depth. So you just do ρgh, you can estimate the pressure. For hydraulic fracturing, usually you need 30, 40 megapascal.
No, I'm wondering that is the mechanism similar when you inject because you make a perturbation of the pressure?
This is not injection. This is just
No,
we don't perturb the medium. This is just propagating a wave into the fluid saturated medium. Right. So what are the mechanisms? So we did full wave computation. We observed some phenomenon. There's a pressure magnification effect. It depends on frequency, depends on geometry, depends on the width of the fracture. And actually, this is related to the slow crack wave studied by many people in early days. So one paper is Frazzini and Aki, and there are many people study this phenomenon. Croaklis. Actually, later on, I found Mike did a lot of work by observing. When I was at MIT, I didn't know. Later on, I found he observed the long period signal in volcano and in geothermal in 1980s. So there's probably among the first observations. So there's this slow wave. Okay, so slow wave trapped in a fluid field, infinite crack. So the difference between my work and their previous work is all the people in previously consider infinite crack, sandwich model. But in my model, it's finite crack. Okay, you have thickness, you have a finite length. For infinite crack, you do not have the magnification. So right now, let's talk about the infinite crack. Okay, so you have a rock, you have fluid, you have a rock. So sandwich layer, and if you have a source, pressure perturbation in a crack, and you're going to generate a symmetric mode Okay, there are anti-symmetric and a symmetric mode. And this is symmetric mode, which means the wave will open the crack, close it, open, close, as it propagates. So you get this wave propagation direction this way, but it close the crack a little bit. And this wave speed is very small. So although we're talking about 1 hertz or 0.3 hertz, so for surface waves, very large wavelength, the wavelength is hundreds of meters. But we're talking about crack, which is on the order of 10 meters. So if you think about intuitively the scattering theory, the 10-meter size object is not going to influence the 100-kilometer long wave, having a 100-kilometer wavelength. But the reason it does affect this is this wave is very slow in speed. Okay, it's tens of meters per second. So that it can reduce the wavelength in the fluid field crack, which is comparable to the size of the crack. So again, the mathematician Crockley first discussed this problem in 1962, and in seismology, Shure, Aki, they did work in 1970s and 80s about this problem. So I'm going to use some kinematic, not the amplitude information, but the phase velocity information to discuss this amplification effect. Okay, here is the phase velocity, group velocity of the slow crack wave, and the group velocity depends on the frequency and also the aperture of the fracture, because they're considered infinite long, so there's no length, just the thickness. So there are 2 characters. One is high frequency wave, high velocity. Okay, we fix aperture and we increase the frequency of the wave. So you can see the group velocity increase as you increase frequency. So that's one thing, is high frequency, high velocity. And the second character is large aperture, high velocity. So in this, we fix frequency, we increase the aperture of the fracture. So again, you have a high velocity. So this is like a highway. Okay, you have a 4-lane highway. It's wider, so you run faster. Okay. So the high frequency, high velocity is, you can consider limit, infinite frequency. The wave is going to propagate in the fluid completely. So you are going to have a fluid velocity, which is 1,500 meters for water. So if we put them together and consider a fracture, so here is a reservoir, here's the wider portion of the fracture, here's the tip. And when you excite a wave propagating from left to right, and because this is white, or a wider aperture, higher speed, so the energy is going to go to the right, higher speed, and this is a slow down. So here is like a red light in the traffic. Okay, you have a lot of cars moving in one direction, and this car is moving fast, and this guy is moving slow. So you're going to have a congestion. So energy build up, increase the fracture pressure. And if you put the waves, okay, this side, single frequency is faster velocity, so longer wavelength. And this side, slower, so it's like a tsunami. So you have really a seismic wave tsunami. And in the open ocean, you got a long wavelength, small amplitude, but on shore, shallow, increased amplitude. But for this wave, this is exactly the same thing. And okay, many people did work about the kinematic, which is the phase velocity, group velocity as a function of aperture. So this is the mechanism. One is why it slows down. It's because the interface phenomena. It's not about the volume of the fracture. It's the interface, fluid-solid interface causes this phenomenon. The second one is a focusing effect. So again, this is representation of the fracture, and you have an incident wavefront. And as the wave propagate, because the wave around the fracture is dragged slow down, so they slow down, you have a concave shape wavefront. And we know that the energy flux is always perpendicular to the wavefront. So therefore, we are going to have a focus effect. And clearly, the focus depends on the geometry of the fracture. So that's the second one. Phenomenon. Of course, the third one is the resonance phenomenon. So that's the mechanism I tried to convince you that there is a pressure surge mechanism which can magnify the incident pressure by hundreds of times, and it can explain weak dynamic stresses. Incident wave is weak, then you multiply a few hundred times, you get a range of megapascal. And then the second one is the role of fluid is very, very important. So if I replace the fluid in the fracture by some solid, there's no such phenomenon. You have to have a fluid. And the third one is it's frequency dependent. At some geometries, low frequency incidence wave do get higher magnification factors. So what are the implications? So implication, of course, we're going to go back to answer the dynamic triggering problem. So if we think, well, the incident wave pressure is 1,000 times several hundred, sometimes 700. We just times 1,000, and you're going to get to a 1 megapascal range. So this is comparable to the stress drop. And this pressure is going to reduce the normal stress, and because it exists, reduce the friction, so you can facilitate earthquake triggering. And actually, Zhi Gangpeng at Georgia Tech, he observed the triggering can repeat itself. It's using surface waves. Every 40 minutes, the surface wave come around, trigger earthquakes, then another 40 minutes trigger. So it's earthquake can be triggered many times. So the second implication, this is a little bit wild imagination, is the kimberlite, how the diamond can come up through like 100 kilometer thick rock. Okay, they are solid. How can they come up in the mantle with under such large confining pressure? So this is a review paper by Wilson and James Head. And the idea is as the magma saturated with CO2 fluid goes upward, and then in the meantime you fracture the rock. Okay, that's but the mechanism is unknown. We just show that this has to be simultaneous. So if we apply our pressure magnification mechanism, if the magma pressure change in this chamber is 0.2, we only need 1/5 of the atmospheric pressure. And if we apply 1,000 times magnification factor, the resultant dilational fluid pressure at the fracture tip can exceed 20 megapascal. Okay, this is in addition to the confining pressure which can break the rock. And it provides a mechanism that can simultaneously fracture the rock while the magma is traveling upward. Third one is hydraulic fracturing. Nowadays, the companies want to know the geometry of the fractures. They want to control fracture. So, using this mechanism, we can control the well pressure, well pumping rate, and maybe we can have a controlled fracturing process by changing the frequency, by knowing the fracture length, and we can incrementally change the source frequency to control hydraulic fracturing. And again, this is very important in unconventional energy development. And in the meantime, so if we turn the problem around, if we have a sensor here, observe that frequency response, we can do a tomography, geomechanic tomography, to figure out the hydraulic fracture geometry, to infer the production decline curve. So this can be a novel subsurface sensing technique. In a way, this magnification mechanism is a sensor, okay, because it magnifies the signal. And the CO2 nuclear waste storage, leakage detection. So third one is related to title of the talk, is how we can trigger earthquakes. So here are the steps. Actually, we try to propose this with Mike. The steps is, first phase is passive listening. Okay, you have a fluid region, let's say geothermal, and you just deploy seismometers on the surface. You listen for a month or a year, and so these red are the geophones. And now, after you do the passive listening, you move the vibroseis to the location of the receivers, to the geophones, and you flip the time trace. Okay, now you're going to do a physical time reversal to send the wave back to the subsurface and then trigger earthquakes, because this focusing will create a large instant pressure, and in this fluid region it will provide additional magnification such that we may be able to trigger earthquakes. And the final words is about earthquake hazard mitigation. The popular idea is to predict when the earthquake occur. This has been difficult. Some maybe 50 years ago, people were very optimistic about to predict the exact timing of the earthquake. And nowadays, most people are doing earthquake early warning. So they're going to detect the initial motion of the earthquake, and then send out broadcast warning to people so they can evacuate before the S wave and the surface waves come. So it's like you're living in this house. Okay, this is like an earthquake going to happen. It's like a house going to collapse. And you are told to live in that house. And we're going to put sensors all around the corners. So once there's a crack, and the sensor is going to send you a message, leave. Okay, that's a warning. And you may or may not have the time to leave.
I think it's a spam message.
So to trigger earthquake is to demolish this building, because nature, as I said, nature has been teaching us how to trigger earthquakes. Okay, the only thing we need to figure out is the mechanism. If we can figure out the mechanism, and we can say, well, evacuate now, and I'm going to trigger it by move equipment, okay, then to avoid hazardous consequences. Because if you don't do this, sooner or later it's going to happen. So if you can say, well, we know from GPS, we know from geodetic measurement, it's going to happen soon, but just the exact time is not known. But if we have a way to trigger it at a predetermined time, that's best. So I'm going to give a hourglass summary of this weak dynamic stress wave and the consequences. So what I did is I start from observation, observed by many people, and then the key thing is abstraction. So we have to figure out what are the key elements in understanding all this phenomena. And then I also talk about several implications and possible applications. So one is dynamic earthquake triggering. These are from observed phenomena. Permeability changes, triggered volcanic eruptions. Well, I didn't really show you examples, but there are many papers and review treatises of geophysics have those. Oil field production increase, low frequency fluid region. So all these phenomena are tied to low frequency fluid regions. So these are all from observation. And the abstraction, which we have to come up with a model to understand all this phenomena, is pressure surge phenomena. So once you have that, we try to understand diamond propagation in solid metal. We hope we can control fracturing process by changing the pumping procedure, and this should be trigger, not induce. So we hope we can trigger earthquakes in a useful way, so at a predetermined time, to really mitigate earthquake hazards in future. So that's the whole talk. So the conclusion is this is a testable hypothesis. So right now we are doing this laboratory verification of the pressure surge phenomena itself. We're not triggering earthquakes, just to verify this phenomenon exists. That's a 2-year project by NSF. And this mechanism seems to be an attractive alternative mechanism to the critically stressed state. It explains transient wave can trigger seismicity in fluid regions, and it also shows there's a frequency-dependent effect. And it shows all these natural phenomena, probably they are connected to each other. They are not isolated, like increased permeability, earthquake triggering, etc. And during this research, we developed numerical modeling techniques and data analysis techniques. I think they can have a pretty wide range of usage. In particular, considering the multi-scale nature of the modeling. So finally, I want to thank for your attention, and you think about this problem again. So 10 coins can trigger earthquakes. Is that critically stressed state or something else? Thank you very much.
Yeah, thank you for the very interesting talk. So yeah, I think the audience have more questions. So Ming?
Yeah, it's quite inspiring talk, and I thank you for that. But one thing I wish you have clarified from this talk is the effect of the size of the impact region. You have mentioned in your introduction, if you dance ballet, you exert higher pressure on ground.
Yeah, maybe smaller force.
But this impact area is so small, nothing is going to happen.
Correct.
Same thing with the classical fraction mechanics. And this small, tiny perturbation can cause infinite stress at the tip of the crack.
Right.
By the theory. But in reality, nothing is going to happen if you just see a small, tiny. So one remedy is that either you calculate the intensity factor for fracture, or more precisely use the generalized J interval. That is a very good way to estimate the size impact on the table. I think your model, and so it's quite really, I think you can go into that direction. Either you develop a dimensionless factor, maybe you can call it a jump factor or something like that, and to really kind of measure the size impact region. Or you can develop something like similar to the J interval. I don't know if it's path dependent or it's independent, but there will be useful way to do that. I think that's quite important.
Right. So actually, this the tip part does have higher amplification, higher pressure, but actually other parts in the fracture also have higher pressure. So it's not just the tip part. So probably I didn't cast my problem very accurately in the beginning slides. It's the entire fracture. Within the entire fracture, the fluid pressure is elevated. So therefore, you try to open the fracture, reduce the normal stress, to have a shear feeder. But I think your point is valid. So we have to also consider the integration of pressure to get a total force. I use those examples just try to give sense of pressure comparison between, in different scenarios.
Does it depend on which kind of surface wave, like relay wave or log wave, which one is dominant or category important?
That's a really good question. In observation, actually, log wave can also trigger. No volume change, correct. But I have to do a calculation to give you a very definite answer to that. But unfortunately, I haven't done the log wave instance in the solid. Yeah.
Also, one more question: are there like intermediate depths earthquake also triggered by this kind of effect?
So like 300 kilometer depth.
50 to 300 kilometer depth.
It seems the triggered crossings are all shallow, just the upper few kilometers. But some people actually suggested that the tremor may be related to fluids in the subduction slab. So this can be deeper than those shallow triggered earthquakes.
Do you know any cases where during hydraulic injections the pump frequency has made any difference in the injection success? I mean, what you're saying is that if you could vary your pump frequency, maybe that's a proxy for pressure.
Yes.
You maybe could do a good hydraulic fracture treatment at lower pressure if you could change the pump frequency. If you could get an oscillation downhole.
I think some companies use pulsed injection. So
Kind of a white?
Yeah, like a series of a delta function, just pulsed injection. So certainly they are thinking about ways to change the pump frequency. Yes.
I'm just curious as to following up that question. How deep do you think these things can operate? Because
Based on the theory, the deeper the better.
but the surface wave, the amplitude is, I mean,
Yeah. Surface wave is going to decrease exponentially.
It's
Yeah.
going to be attenuated quickly.
But the reason is if you go deep, for example, 300 kilometers, the confining pressure is so large, and any magnification, you can achieve very large perturbation stress perturbation, but the perturbation of the stress is still orders of magnitude smaller than the confining pressure, and therefore we can still use acoustic waves or elastic wave equation to describe this phenomenon. For example, if we're under 400 kilometers, so we're going to get in maybe 10 gigapascal confining pressure. But in order to break the rock, we need 20 megapascal. So if you compare 20 megapascal with 10 gig, it's still small. It's still within the acoustic approximation in the equation. But if you go shallow, and you cannot break the rock because 20 megapascal is like a confining pressure. So there's no way you can, and you have to change the equation. So in that case, the physics is completely different, I think.
But this such phenomenon, you need some size of the reservoir. So in the deep part, you actually changing the size of the reservoir.
We can get rid of the reservoir part, just to have an isolated fracture there. Yeah, this one is really for the convenience of the boundary element modeling. So we want to use one boundary to separate the two medium.
If you have only the isolated fracture, then your focusing effect,
That's also one boundary separating two medium, but in that case, the boundary element will have a fictitious resonance frequency. And at those frequencies, you mean the matrix are not invertible. But now we have a way to solve that resonance frequency problem. But this work is done before we got the new algorithm.
One more last question. Helium?
Yeah, for magnitude 6 or 7 earthquake, you have like surface wave around 20-30 seconds period.
what's the aspect ratio of the fracture?
So 20 seconds times 3 point something, that's like 70 kilometer wavelength, right? And this fracture is a meter scale. So, it's 10 to the 5th meters wavelength compared to 10 to the 1 fracture size. So that's 4 orders magnitude difference.
Is this something we can expect in nature?
Yeah.
1 meter wide fracture?
Well, not 1 meter wide. The width of the fracture is even smaller. It's millimeter. So it's 10 to the minus 3. So compared to the wavelength, that's 10 to the 7 order magnitude. If you just directly compare the wavelength versus the fracture width or the aperture. So the issue here is, if you reduce the fracture width, the slow wave is going to go slower. And in theory, if you reduce the fracture width to 0 millimeters, the velocity is 0. So therefore, the thinner the fracture, the shorter the wavelength is. But of course, when I said 70 kilometer wavelength, that's the wavelength in the solid rock. It's not the slow wave interacting with the fracture. But if you look at the slow wave, the velocity is 2 orders of magnitude smaller than the velocity in the rock.
So yeah, let's thank Professor Zheng again.